Hello and welcome to the series of SystemVerilog for verification short videos. Today we'll start with some basic data types of SystemVerilog. I have divided this topic into 2 to 3 parts. Let's start with the first part. So agenda of today's lecture is covering logic, data type classification, groups of data object, and net. The prerequisite of today's lecture is having basic knowledge of Verilog as well as having some knowledge of any programming language, say C. This will make you understanding system Verilog a lot easier. Let's start with the first topic, logic. In Verilog, we were used to work with the data types like reg, wire, etc. But here, logic replaces reg. Why? Because reg keyword was getting too much confused with the word flip-flop. User was not able to understand whether reg will directly mapped with flip-flop, latch, or any other thing. So here, user doesn't need to worry about that. Logic can be net or reg depending on the usage. Logic is having four state values 0, 1, x, and z, in contrast to two state values which are having only 0 and 1. Here 0 means logic 0 or a false condition, 1 means logic 1 or a true condition, x means unknown logic or say don't care, and z means high impedance or say open connection. Each four state value is equivalent to some two state value. 0 and 1 are equivalent to 0 and 1 only, but x and z gets equivalent value zeros in two state. Okay. The advantage of having logic as data type is there is no need of port list tools. We will look at this statement in actual code. So here I am having one file in that one module named 1 bit, which is having some bit operation, say z equal to a plus b. I am having another module named 4 bit. Here I have taken 4 instances of 1 bit and made some connections. Here, as you can see, that z has to be type wire because it is being driven from the instance output port. On the other end, A and B has to be reg type because they will be passing some values to 1 bit and we may need to store them into the 4 bit. So let's enhance this example with assigning some values to A and B. So what I'm doing is I'm making assignments for A and B, and then we will see the value of z. So I'm taking a equal to 4, b equal to 1, and then I want to display the value of z. So I'm making z equal to percentage 0d and z. The syntax of this dollar display is somewhat similar to printf, so make sure of the syntax. Will need this syntax to display the value onto terminal. Let's compile this code with Verilog vcs plus v2k logic.sv. Okay, so it's compile clean, and let's simulate with dot slash simv. Okay, so here I'm having value z equal to 5, so it's running perfectly. But now if I change this wire to reg by mistake, suppose, and now recompile the code, see here I'm having error that this is invalid connection, you can't do this. This makes a Verilog little bit confusing. Rather now, if I prefer to having both just logic, so I'm making both keyword as logic. Now we'll compile this code with system Verilog. So to say VCS that this is system Verilog, I need to add a switch named -s Verilog and then file name. Now let's compile this. Yeah, it's compiled clean. Now I'll run this with the same dot slash simv, and I am able to get the value z equal to 5 here. So if I'm having just one keyword logic, I don't need to worry for wire or reg. I can give anything. One more example, we will look for this equivalent two-state value. So now what I'm going to do is I will have one logic C, then let's say one bit, which is, we'll go through this data type later on, but this is two state data type bit D. And I'll make one more procedure, initial begin, and let's give C a value 1bx, then assign D equal to C, and let's display the value of D. I'll say percentage B because I need to know the bit D. So now let's compile this code. vcs-sverilog logic.sv. Okay, it's compiled clean. Now let's run this. Okay, it's showing b equal to 0. So as you can see, this 1bx got converted to 0 as x is having equivalent value 0. All right, the next topic, data type classification. Here, data type are classified into singular and aggregate data type. Singular means a single value or a symbol or a handle. On the other hand, aggregate means a set or collection of singular values. What does it mean? Any unpacked structure, unpacked union, or unpacked array are aggregate type, and anything that is not unpacked, say integral, string, class object, they are singular. Though singular can be sliced into other singular subparts, but they will be called singular only. Now, what is the need of classifying this such that singular data type can refer as collective group, or say they can be treated as a single vector? We'll also look on one example for this, so you will be able to understand more like what is aggregate and what is singular. Let's come to this example. Here I have taken one structure. We'll also go through this structure data type later on, but here is just one example to understand packed and unpacked difference. So here I've taken structure inside that one logic and one byte, the named struct unpacked. One another struct with keyword packed, which makes is packed structure. I have taken another logic, another byte with name struct packed. Here is one variable of 9-bit named variable. So if I see at the size of this structure, 1 bit plus 8 bits, so 9 bit, and here also variable is having the same width. Now what I am planning to do is, I know that packed structure can be referred as a single vector. Let's try. Now I want to assign the value of this variable directly to this struct packed instead of accessing individual logic and byte. So what I will do, I will make one procedure, and now I'm assigning some value to variable equal to say 5, then struct packed equals say variable directly. Okay, and now I will display say s equal to percentage 0d struct packed dot say w. So now I'm displaying this w. Okay, that's it. Now we need to compile this one. Let's go to that folder. Okay, and let's compile this code. Okay, it's compiled clean. Let's run this. It's showing me as equal to 5. So here structpack.w is having value 5, which was from the variable. So here I was able to assign the value of variable to a structure considering structure 1 vector. On the other hand, if I replace here packed by unpacked, which is a structure of unpacked, I'm expecting error. So let's compile this code. Yes, we can see here is error. It's saying incompatible complex type assignment. So I can't assign some unpacked value directly from some variable because it is not a single vector. Okay. Now we'll understand this concept with respect to memory allocation. When I'm saying singular data type, suppose the same structure. Now S and W, when they are assigned a memory, they have to be assigned a location of side by side. So this is say S and this is W. So when I say I'm accessing a complete structure, it will consider this total memory as one vector. On the other hand, when I say aggregate, I'll be assigned some location, one here, another anywhere, say this place. So when I try to assign it to a single one, I won't be able to connect this place to say this place. All right. The next topic is groups of data object. Based on the way in which they are assigned and hold values, there are two groups: net and variable. Net. It can be written by one or more continuous assignment. It can't be procedurally assigned and it cannot store a value. Basically, it is just an interconnection between two variables. We can say that. On the other hand, variable, it can be written by one or more procedural statement. It can also be written by one continuous assignment only once. And it can obviously store and holds value. And the last written values will determine the actual value. Okay. We'll look at the variable in the next session. In this session, we are targeting to have all the sub types of net. So we'll now go through net. Net is having two classification: built-in and user-defined. If we talk about built-in net, it is having 12 different parts: wire, try, uwire, w or, w and, trior, triand, tri-reg, try0, try1, supply 0 and supply 1. We will go through each of them with some explanation and code running in terminal. So let's start with wire. Wire means it is driven by a single continuous assignment. Means one variable is assigned some value from other. On the other hand, try, it is having multiple drivers, driver net at the same time. So what I mean to say is, when I'm talking about driver, there is one input, there is one output. And when I'm saying about try keyword, it is having basically a tri-state buffer as hardware, where there are three states. There is input, output, and one enable signal. When enable is 1, whatever my input is will get passed to output. So 0 to 0, here 1 to 1. But when my enable is having value 0, doesn't matter what my input is, my output will always be Z, means high impedance state. So there are three state: 0, 1, and high impedance. Okay. And now when I say multiple drivers, what do I mean by multiple drivers? It means at the same time more than one is driving variable or driving some value to one variable. Okay. So now here there should be some conflict, and based on that there should be some resolved value which will be passed to output. Now for wire and try, we are having some truth table. What this truth table says us is, if the one driver is passing value 0 and other is passing value 0, the output will be 0 only. Similarly, if one is passing 1 and second driver is passing value 0, my output will be X. Accordingly, I am having 16 possibilities for 401XZ from one driver and 4 possibility of 01XZ from other driver. Let's try to understand wire and try with some SystemVerilog code example. So now here we'll start with some code. What I'll do is I'll declare one wire named A, one try data type named data, some logic, say bus 0, bus 1, and some selection line. Okay. Now I'm assigning to y, say a equal to bus 0. So I've made this assignment of wire same as verilog. Now I will make one assignment for try, say assign data equal to selection line. If 1, it should be bus 0 or 1BZ, so high impedance. Okay, so I am here trying to make equivalent code for this tri-state driver. Now let's just initialize some value. So initial begin, and I'm giving bus 0 equal to 1B1, bus 1 equal to 1B0, and let's take S equal to 1B1 for now. What I need to print is for a display, and I need to print A equal to percentage B, then data equal to percentage B, A, and data. Alright, let's compile and run this code. VCS -sverilog and example.sv. Okay, it's taking time for compilation. It's compiled. So now let's run SystemV, and the result is A is 1 and data is X. A is 1 and data is X. If okay, one more modification, I will display after #1 just to make sure that all these statements have been initialized before the display occurs. So let's try to compile it again and run it. Yes, now I am able to have A equal to 1, data equal to 1. My A, which was having bus 0, it is 1, and my data, which was having S, that is 1. So the first value of tri-state will be taken, that is bus 0, which is again 1. So my A and data both are 1. Now if I'm making my selection line S equal to 0, I should get this Z value on data. So let's compile and run once again. Compile clean, running it. Here A equal to 1 and data equal to Z. So I got two different state for data over here. This is it for single driver wire and single driver tri-state. Now when I say that I'm having multiple driver and it's following this truth table, so let's check it out. Here I'm giving one more assignment to A named bus 1. This is my wire multiple driver. Similarly, let's make here data multiple driver, and here I'm making two different selection line S0, S1 and bus 1. Okay. So first of all, I need to declare S0 as well as S1, and here I need to give some S0 equal to 1B0 and S1 equal to 1B1. Let's give both S0, S1 as 1. Now both are having 1, so data will be driven bus 0 and bus 1, which are having different value. Let's see what happens. Let's compile this code, compile clean, and now let's run it. Here my A is X. Let's first check what happens to wire multiple driver. A equal to bus 0, bus 1, so 1, 0. According to my truth table, if 1 is 0 and 1 is having value 1, output should be X. So that's correct. That's following the truth table. And for try, again, my S0, S1 both are 1. Bus 0 is 1 and bus 1 is 0. So again, one is 1, another is 0. So X should be my output. That's what I'm getting. Now let's make any one 0 and let's see what is happening. Compiling it, and let's run. Now my A is X, data is 0. Let's see what was expected. I didn't change anything in A, so it's X only. Here I made S 0 equal to 0. So 1 is Z, another one is bus 1, that is 0. So Z and 0 combination. Z and 0 combination output should be 0. Here I am able to have data equal to 0. So here I am checking each and every combination of wire and try with multiple driver. This is it with wire and drive. Next is uwire, means unit driver wire. This allow only a single driver. Means if we'll have multiple driver with definition uwire, it will give us an error. Next is WOR and trior. This says that when any of the drivers is 1, the resulting value of the net will be 1. So if I look at the truth table of say WOR or trior, that is T3, here whenever one value is 1, I'm able to see the output is 1, as well as here whenever one driver drives 1, my output is 1. For other values, it will follow the truth table or of wire or try. If I want to try this, I'll just replace this wire by WOR, and I'll not change anything else for now. Here bus 0 is 1, bus 1 is 0. So I should get output equal to 1 because one driver is already 1. Let's compile it and run that. Yeah, A equal to 1. So because I chose WOR and one driver was having value 1, my output is 1. Okay. Similarly, trior. It is the similar fundamental for tri-state. Here I will replace tri with trior, and now I will keep both of them as selection equal to 1. So bus 0, bus 1 will get selected, and they are having one value 1, another 0. So I should get 1 in the output again. Let's see the output. I'm able to have data equal to 1. So it's following truth table perfectly. This is how we declare and we use W or try or etc. Similarly, the next fundamental is W and triand. Here, wire AND is happening. So if any driver is 0, the value of the net should be 0. I will just check with W AND once. Here I'll replace W or with W AND. I'm having one value 0 and 1, 1. So my output should be 0 in this case. It's compiled and running it. My A equal to 0 proves that WN is working perfectly. So this is how all of these variables wire, try, U wire, W or try or WN, try and will work. And next will be the exercise for this net. Here, you will get the definition by this slide, but I will explain that shortly. In first exercise, take 2-bit vectors A and B, say A1 down to 0, B1 down to 0. Write a SV code that verifies all the possibilities of below block diagram. Block diagram says that for A of 1 down to 0, there should be wire AND of A1 and A0, which is small a. For B, it should be wired OR of B1 and B0, it is small p, and A plus B should be happen, and Z should be your output. And you have to check all the possibilities of A and B considering 4 state values 0, 1, x, z. For an example, A is 0, 1, B is x, z. What should be my output? And verify AB with the wired AND, wire OR truth table respectively. A with wire AND and B with wire OR. So you will get all of the exercise required for this wire OR and wire AND here. Exercise 2. Here we will take a sample version of STA line of I2C protocol. If you will go through I2C protocol, you will find that SDA line is a common, and master and slave both are driving onto that line one by one. So here we will not make the complete protocol, but we'll make a small program which will be following the same behavior. What we'll do is make one master and one slave module. Take inout try port SDA. SDA is inout because it can't be just input or output. It has to be inout and it has to be try in both of them. So in master and slave, I'll be having one inout try port named SDA. Connect both module in top module having wire SDA. So in my top module, I have connected or say taken instance of master as well as taken instance of slave and connected their SDA with one other wire named SDA in top. Now we have to make a state diagram having two states in both master and slave individually, such that in first state, master should be driving on SDA line, means master is driving something onto SDA and slave is receiving it. In the second state, the reverse one, means slave should be driving something on SDA line and master should be receiving the same. And we have to try with this example with try, triand, and trior, everything. A hint is that both modules will be having their individual enable signal and individual SDL line. And another hint I'll provide is whenever master is accessing bus to drive it, slave will leave the bus by having high impedance state, and vice versa. Means when slave will access the bus to drive something onto it, master will leave the bus by having high impedance state. Okay. Next data type is tri-reg. This data type is used to model charge storage nodes. This is the only net type declaration which is having the functionality of storing some value. It is having two states, driven state and capacitive state. In driven state, at least one of the drivers should be having value 0, 1 or x. In that case, resolved value will get propagated and will get driven as normal net. But in capacitive state, if all drivers are having value Z, that is high impedance, then it should retain last driven value and Z should not get propagated to output. Here is one example for that. Suppose this AND gate, then we have one NMOS, here is another NMOS, here it's wire A, wire C, wire B, and here is tri-reg D. So what should happen? At simulation time 0, suppose this wire A is having 1, wire B is having 1 value, wire C. Now because these both are having 1, both NMOS are on. So my wire C is directly connected with AND gate. So it is having strong value 1. So it is having strong value 1. And similarly, because this NMOS 2 is on, my tri-reg D is also having the same strong 1 value. You can see that here. Now after 10 nanosecond simulation time, suppose wire A is 0. So this NMOS is off now. And wire B is the same state, that is 1, that is on. Now what will happen? This AND gate will not get directly connected to wire C. So my wire C will be unconnected having high impedance value Z. And this wire B is 1, so NMOS 2 is on. My tri-reg D is directly connected to wire C, so it is having connection of high impedance, and it will be in capacitive state where it should retain the last value, and Z means high impedance should not get propagated. So my D will be having the previous value which was strong 1, but now it will be having the value 1 only with medium strength. That's it. Next two data types are tri0 and tri1. Tri0 is used to model nets with resistive pull-down devices onto them. Means when no driver drives a tri0 state, it is having value 0. We can directly see it in the truth table that whenever both are having not connection with the driver, means both are having Z, my output is 0, means pull down. On other hand, tri1, which is used to model nets with resistive pull-up devices on them, means when there is no driver, it drives a tri1 net means its value is 1. So here I'm able to see whenever no one is driving, means both driver are having z value, my output is 1, which makes it try 1. You can try this try 0 and try 1 by your own in the same exercise as before of I2C. You can take the variables at try 0 and try 1 and check the output and compare them with the truth table. So this is it for this session. We have completed all subtypes of net declaration. In next session, we will start with variable data type. And for this exercise, if you have any confusion, you can ask the questions into the comment area. Thanks a lot. See you in the next session.